Now we're going to do 9.3, and that is on logarithmic functions. Last week we learned about exponential functions, which had the form f of x is equal to a constant base and a variable exponent. Logarithmic functions are the inverse of exponential functions. They undo them. So just how division undoes multiplication and subtraction undoes addition, logarithmic functions are going to be the reverse of exponential functions. So, or the inverse of exponential functions. So, just like we just learned that the inverse of a function is the reflection of a function on the line y equals x, we can draw a exponential function. Remember we did this, draw some straighter lines. We did this a week ago. We had exponential functions that started with a slow increase and then grew exponentially, explosively. If we were to reflect this across the y equals x axis, what that would look like is an initial fast increase followed by a slow increase that gets slower and slower. That's a logarithmic function. So let's see what it looks like. Let's take the inverse of this f of x function. We'll replace f of x with y and write that y is equal to 2x. Now we reverse the variables. That's going to give us that x is equal to 2 raised to the y power. But now we're stuck. We don't know exactly, we don't have the tools yet to evaluate this or to isolate y by itself to solve for a function of x. So today we're going to learn about logarithmic functions that allow us to do that. So if I were to read this function to you, I would read that y is the exponent of the base 2 that gives us the variable x. We can rewrite this and say that y is equal to the logarithm base 2 of x. What this means is that y is equal to the exponent of a base 2 that gives us x. Now, this is kind of confusing. So we're going to do a couple examples to help you get familiar with this logarithm form. So we're going to convert a couple exponential forms to logarithmic forms. Let's say we had the exponential form 2 raised to the third power. We know that that is equal to 8. Now when we convert that to a logarithmic form, that would be written as the logarithm with a base of 2 of 8 is equal to 3. So to do this slowly and to break it down, we would identify what we have, we identify the pieces and put them where they belong. So we're asking, when we're writing a logarithm, we're asking a question basically. What is the exponent that we're going to apply to a base to give us 8? So what exponent are we going to apply to 2 to give us 8? Well, the answer is 3. So when we convert this into this, we're going to begin by writing down our log function. Now we're going to leave a space, and we're going to write an equal sign. So we know that we want to find the exponent. So we're going to go over here. We're going to identify what our exponent is. In our case, it's 3. And we're going to write that our logarithmic function is equal to 3. Now we need to find the base of the original exponential function. The base is 2, so we look over here, the logarithm, well, we're going to give our logarithm a base of 2. That means the only other number that we have to work with is this 8, so we can see that it just goes right here. Now let's do that again. Let's say that we have 5 squared. We know that 5 squared is equal to 25. Well, we want to ask the question, what exponent do we need to give to 5 to result in 25? So we're going to write our log, and we're going to set it equal to something, leaving a space here. Let's go over and identify our exponent. Our exponent is 2, so this is going to equal 2. Now let's identify our base. The base of this exponent of 2 is 5, so we're going to write a log base of 5 here. And now the only other number is 25. So we have converted this exponential form, 5 squared equals 25, into a logarithmic form. The log base 5 of 25 is 2, which means that the exponent that we have to apply to 5 to reach 25 is 2. Let's do one that involves variables. What if we had 10x was equal to 7 in exponential form, and we want to write that in logarithmic form? Well, again, we're going to write down log, and we're going to set it equal to something. Let's identify our exponent. Our exponent is x. Our base, we identify that as 10, so we're going to write a log base of 10. And our the only other number that we have to work with is 7, so we're going to write a 7 in for here. And now we've converted 10 raised to the x equals 7 into logarithmic form. We can also go the other way. For example, if we had the logarithmic form log base 4 of 64 were equal to 3, and we want to write that in exponential form, let's just identify what we have. So our logarithm has a base of 4. That means our exponential function is going to have a base of 4. It's equal to 3. That means our exponent is going to be 3. And the only other number that we have to work with is 64. So we're going to write that in right here. And we can calculate this to verify that it's true. 4 cubed is 64. And we can do this one more time with the logarithm of base 5 of 125 is equal to x. If we want to write this in exponential form, we identify our base of the logarithm, that is 5. We identify our exponent, it's equal to x, so we're going to say 5 raised to the x power is the remaining number, 125. So now let's learn how to solve some of these. So let's say we had the logarithm base 3 of 9 equals to some variable n. Or even if we were just given logarithm 3 base 9 and we were asked to evaluate it, we want to find out what that equals to. We can set it equal to any variable, could be x. We're going to use n because that's what the chapter is using. We're asking the question, what variable do we have to raise a base of 3 to result in 9? Now, you may be able to recognize just from knowledge of perfect squares that we would have to square 3 to result in 9, giving us an n of 2. But it's not always going to be as simple as something we can look at and just see. So what we're going to do is we are going to convert this to exponential form and then solve. So converting this to exponential form, our logarithm's base is 3, which means we're going to convert this to have a base of 3 raised to our exponent n and set it equal to the only other number, 9. Now that may not help us a lot, but we can the method we can use to solve for n is we can get similar bases, basically meaning we want the base to be equal. And we can do that with 9 by simplifying it into 3 squared. So now we have that 3 to the n power is equal to 3 squared. And once we have similar bases, we can set the exponents equal to each other. So we would just write a new equation that n, the exponents on one side, are going to equal to the exponent on the other side. So we can see that n is equal to 2, which means that when we raise 3 to the 2 power, it gets us 9. Now let's do this in an example that isn't easy to see right away. If we had the logarithm with a base of 4 of 2 is equal to some number n, we don't know right away what we can raise 4 to the power of to result in 2. So we're going to begin by converting this to exponential form. We identify our base. We have a base of 4. Let's identify our exponent, that is n. We're going to set it equal to the remaining number of 2. Now, we want to work our numbers so that the bases are equivalent. Well, we can look at this 4. We can convert this 4 into 2 squared, right? And that would give us 2 squared to the n power is equal to 2. Well, we know from rules of exponents that 2 squared raised to the n power is the same as 2 to the 2 times n power, and that's going to be set equal to 2. And we also know that any number raised to the 1 power is equal to itself, right? And now we have an equation. We have similar bases, and we have an equation for the exponents. So we're going to set them equal to each other. We have that 2n is going to be equal to 1. That gives us that n is equal to 1/2, effectively saying that when we take 4 and raise it to the 1/2 power, that gives us 2, which makes sense because we know that 4 raised to the 1/2 power is the same as saying the square root of 4, which is 2. Let's go over some general rules for logarithmic functions. So let's say we had a logarithm of base 5 of 1, and we want to evaluate it. We want to figure out what exponent we have to raise 5 to get 1. Let's convert this to an exponential function. That is a base of 5 raised to the n power is equal to 1. We know that anything raised to the 0 power is equal to 1. That means we can rewrite that 1 as 5 raised to the 0 power. Now, we can set the exponents equal to each other and get that n is equal to 0, which gives us a general rule that anytime we have the logarithm of 1, it doesn't matter what the base is, it will always equal 0. Let's look at something else. If we had the logarithm of 5, base 5 of 5, and we want to figure out what that is equal to, we can take the, as a general rule, I should have written an n there, I got ahead of myself. We can just remember that anytime we have a log of a base of the same base, it's always going to equal 1, but let's prove it. So our base is 5, our exponent is n, and we're setting that equal to 5, well, 5 is the same as 5 to the 1 power. That means n is equal to 1. So we can just say as a general rule that anytime we have a log of a certain base to a log of a number of a certain base that's the same, it's always going to equal 1. I'm going to do another example really quick, and then we'll teach you how to do this on your calculator. Let's say that we had the logarithm of 0.01, and we set that equal to n. Now, we may not know how to solve this right away because we don't have a base on our logarithm, and that's going to lead us to a rule that we just have to remember. Anytime the base is not specified in a logarithm, the base is always 10 because the default logarithm has a base of 10. Now, if we were to evaluate this, we would say that our base of 10 raised to the n power is equal to 0.01. This is kind of hard to do, but let's try to rewrite this 0.01 100th in a way that we can work with. So 0.01 100th can be rewritten as 1 over 100, and that can further be rewritten as 1 over 10 squared, right? And then we know that anytime we have an exponent in the denominator, we can flip things around and make that exponent negative. So that can be written further as 10 raised to the negative 2 power. And now we have a relationship with similar bases. So we can write that n is equal to negative 2, right? So we see that in order, the exponent that we have to apply to a base of 10 to get 0.01 is negative 2. Let's try to do that on the calculator. Now, if you have a scientific calculator, go ahead and pull it out. Look around. You will see a log function. It's just log, but there's no base attached to it. Remember, the default logarithmic function has a base of 10. So, on a scientific calculator, if you wanted to evaluate this expression, you would first type in 0.01, and then you would hit the log button, and it would give you the result of negative 2. On a graphing calculator like mine, you would first hit the log button, then you would type in 0.01, then you would hit enter, and that would give you n equals negative 2. So remember last week we introduced a new constant, e. This was Euler's number. Now we're going to actually see why it's significant. E is useful in logarithmic functions because it's a common base of them. So what that means is we often see logarithms with a base of e. So we might have the logarithm of x base e. It's so common that we have a special term for it. We could rewrite log base e of x as the natural log of x. You might even notice there's a button dedicated to this on your calculator. With natural logs, all of our previous rules still apply. So like the natural log of 1 is equal to 0. The natural log of e, well, that's just the natural log base e of e, so that's equal to 1. And then a rule that I forgot to mention earlier was that whenever you have the natural log, I'll back it up. Whenever you have a logarithm of a base of a number that is the same as the base raised to a power, if you evaluate it, you just get the power. And we can we have that with natural logarithms as well. So like the natural logarithm of e raised to the fourth is just evaluated as 4. Now, if we were to graph a logarithm or a natural logarithm, we'd see that all of our transition's not the right word. All of our transformation rules still apply. So I'm not going to write them all out in detail, but like if we were to have the logarithm of x plus 2, we're adding 2 after the function of logarithm. That means we would take our logarithmic function that looks kind of like that and just move it up by 2 units, right? And if we were to have something like a logarithm of x minus 2, right? Our rule of moving to the left and right still apply. Minus 2 means we're moving to the right 2 units. So we would just go over here by 2 units and draw the graph again. And then the whole reflecting about axis rules for having like a negative x or a negative function, those all apply the same way that they would with exponential functions. The last thing I want to talk about in this lecture is, let's say, so remember from earlier, one of the first examples we did was that a logarithm of 8 with the base of 2 was equal to 3. But we didn't know that it equaled 3, and we want to use a calculator to evaluate this. Well, remember, on our calculator, we have a log with a base of 10, and we can't enter our own base. The calculator always uses a log base of 10, which might make us out of luck if we were trying to evaluate this expression. However, what we can do is we can take 2 log base 10s to evaluate this. So we would make a fraction, and we would have the log base 10 of 8, the bigger number, divided by the log base 10 of 2, the smaller number. And when you put this into your calculator, you're going to see that the answer is 3. And if you remember, that means that 3 is the exponent that we apply to 2 to get to 8. And we can also write this in natural logarithm terms. So if we were to take the natural logarithm of 8 and divide it by the natural logarithm of 2, it would also equal 3. That is the end of 9.3 content. The homework for this section is going to be even problems through 48.